But my name's Adam Zelny. I'm the applications specialist with AET Labs, and I am out in the field a lot working with our sales team to everything from kind of consulting with customers on the systems we sell and install to doing the installations and getting our end users onboarded to those systems. And today our feature is end of arm tooling with universal robots, and we'll get a little bit more into that. But yeah, if we could just go around to our AT folks, you want to do some introductions? Dave?
Hey, Dave Kempski, AET Labs, here in Essex.
Dave is AET's founder. Matt?
Matt Campbell, technology consultant. I work in Eastern New England, primarily higher ed, but have some high school and community college accounts as well.
I just want to say too, hello to Jennifer from MIT. Jennifer, I've never seen your face before because I don't think I've been on campus to have the chance to see you, but I see your name a lot from the architecture department there. So great to meet you virtually, and everyone else too.
Chris
Macrina, technology consultant, primarily CTE schools throughout Rhode Island, New England, New Hampshire, and Massachusetts. Welcome, everyone.
Kristen?
I'm Kristen. I work in marketing for AET Labs, and just want to let you all know that you'll be getting a recording of this tomorrow. So look out for that email.
Thanks. Kristen is our kind of like coordinator behind these meetings and big help with getting them going. Okay, Jen, since you're on video, would you like to jump in and introduce yourself?
Is this working?
It is, yeah. Yep.
Okay. It doesn't always work.
We got it.
I can't see who I'm talking to. I'm not used to using this type of meeting software. We're more of a Zoom crowd. Sorry.
Sure.
Okay. I'm a shop manager and shop instructor over at the architecture school at MIT. I've been here for about 12 years now. And we're actually very small, which I think is not what most people expect. And in the time I've been here, I've had no time to put any effort into robotics at all. So I just need to start learning what options we have. Because if I don't do it, we don't really have anyone around who has the time for it. So I want to do anything I can to make time to start figuring things out. We have a new building that's opening up sometime in the next 10 years, and there will be more space. And I will be asking for more money for machinery, so I need to do research on what to invest in ahead of time.
Excellent. Well, happy to have you for certain. And if you're new to our Tech Tuesday meetups, we make our best effort to do these every month throughout the school year. And we'll change the subject every month usually, or change the machine in that case in the workflow. But it's pretty much an informal kind of discussion. We always call it demo and discuss because I will oftentimes demo a specific feature of a system, and I'll invite people to talk about it and kind of informally chat about it. Today, Dave's going to give a quick presentation on our topic. Last month, we were also working with universal robots, and that was more of a general overview of the system. And if you're someone that is new to universal robots and you want to know more of the kind of fundamentals, we're not getting into that too much today. If we have time, I'll answer any question you have. But you can always reach out to us, and if you want like kind of a virtual demo, or you want us to answer, get more into details on the system. In any event, our topic today is end-of-arm tooling. And if you are unfamiliar with end-of-arm tooling, Dave Kempski is going to just give a little demonstration or a presentation on what that is. So go ahead, Dave.
So I just want to thank Essex Tech for allowing us to host this event at their school. They purchased a couple of UR3s a few years ago, and Adam is in one of the classrooms. They've allowed us to do this webinar there. So thanks so much, Patrick, and the rest of Essex Tech. So let me share my screen. Okay, so my background, by the way, is in industrial automation. Before starting AET Labs, I worked for a couple of different companies in the industrial automation space. I was an applications engineer, and then I worked for a larger corporation, got involved in corporate training, and eventually was kind of spearheaded a national effort in systems for education. So I've been in this space for a while, and I really like it. I really enjoy it, and so I have a little bit of knowledge here, but just enough to be dangerous. Intro to end of arm tooling. So, in talking about this, end of arm tooling can be broad in what it does, but in this context, we're talking about the end of arm tooling for robots. There are other types of, I guess they could all be considered robots, but in this case, we're thinking about like 6-axis robots, and generally we refer to our universal robots because of their simplistic nature and just endless capabilities. But what is end of arm tooling? Well, it's what enables a robot to do work or tasks. In this case, we're just kind of showing, we're going to do some work. We're going to pick up this box and we're going to move it. We're going to use vacuum pads to make contact with the box and move it. Could also have some kind of end of arm tooling that would do a task. This is kind of a crazy multi-tool end of arm tool effector, or end of arm effector. So it can really be, anything creative, any kind of creative design. And the thing about with Universal Robot, in this case right here for end of arm tooling, I look at this one with these multi-tools on it. This is what the collaborative robots have kind of enabled this for people to become more creative and think of these just wacky ideas of what to do with the robots. So you would never see anything like this on an industrial robot, just because of the nature of industrial robots. They need to be behind cages, and they're just not as able to switch between applications as easily. So end of arm tooling. What makes up an end of arm tooling? Well, they're all different, but in general, you're going to have some kind of a transition plate between the end of arm tooling and the robot itself. So it might be whatever it's got to fit the design of right at that wrist. So it's going to generally be something that's strong. So it's going to be made out of could be aluminum, could be 3D printed as well. You're going to have some kind of energy source. So that would be either electrical or air. Sometimes this is channeled through the arm of the robot. Sometimes there's a valve right within the robot too, so it's nice for keeping things clean. There's a sensor, so there's something that needs to detect if it's picking something up. It needs to know when to tell the robot to move. And of course, the tooling. And this could be, again, anything. Most common, you're going to see grippers, you're going to see vacuum pads, but as you start to research it a bit more, there's no end to the types of tooling that can be out there. So some considerations when designing end of arm tooling or coming up with an application is the application, of course, and what's the cost? What's the development time? So they can certainly get, sometimes need to be a lot more. There needs to be something that if it's placing the item into a fixture or something, there may need to be something that holds it, so you need to design that. So there's a lot that can go into it. The energy source, of course, if you've got do you have the air supply? So if not, if it's not as convenient, you need to provide some kind of electrical source, which is great for what we're talking about today, because Robotiq has these really nice end effectors that do not require an air source, but they are more expensive for sure. The sensor, again, no go, go, whatever it might be. So Safety, what are you going to have on the end of this robot flinging around? Is it going to be something sharp? I mean, even with collaborative robots, they will stop when they sense if with the force sensors, but if there's something sharp on there, that could still hurt you. So it makes a difference. So keep that in mind. Weight, and this is a big one. So with the weight, you're really going to either increase the cost because you need a larger robot to pick up that end effector. So you want to look at ways to reduce the weight. One of the ways of doing that is with 3D printing. So 3D printing has just become a standard for a lot of manufacturing engineers. And main reasons are because to make them faster, you can design them faster, put it that way. You can make those fixtures lighter, so you don't need as large of a robot. So everything that costs less, you're not going to machine them. The costs involved are much lower, and you can do a lot more in terms of the customization. You can funnel channels through the tool itself to allow for air. In this case, they're using tubes, but you could do that in some cases. So there's a lot of things you can do with it when it's 3D printing. So it's really, if you're doing anything with 3D printing and you're going to meld both robotics and 3D printing, it's a great combination. So we can't talk about end-of-arm tooling without talking about applications. Applications drive usage of the robots. Here are some standard, let's call them standard industrial applications. Machine tending, just basic material handling. They're moving a door in this case. Assembly and dispensing, welding, packaging, palletizing, metrology, inspection. They all have their own specific uses. They all have specific end-of-arm tools on that. So with applications driving usage, these applications, especially with cobots, cobots drive creativity as well, and we've seen that in a number of different through a number of different companies that work with Universal Robot, and just people, the way they use the robots, because they are not bound by a cage and they can collaborate right next to another person. The designs are so much more creative. These right here, what we're looking at these are solutions that can be used in an educational space or in an industrial space, but the one on the left you're seeing is what we would integrate for a machine tending application. This thing will roll right up to a Haas mini mill, and with a little bit of integration work, we have a kit that we would use to integrate that in. The end effector on it might be a gripper, but it might be a specific type of gripper. In fact, it would probably be a dual gripper, and which makes it so much more efficient. So it will pick up the raw material in one finger, and as it brings it over to the machine, the door opens up. It removes the finished piece, flips around and puts in the raw material, and that makes it so much more efficient. It comes back out. Metrology and inspection. This is really cool because of just small pieces and the delicate nature of that. Adam's going to demonstrate a little bit of metrology that's built into what Robotiq has in their grippers. And then this other application over here you're seeing is Vectus, and that is a application for cobot welding cell. So all different types of end effectors. And there are these universal application kits. These UR Plus is a part of Universal Robot, and what they have are these third-party companies like these. There are more of these on Universal Robot's site. I will not go there because I could spend hours there. It's really cool. You see so many different creative designs, and so that's where it's come out of. The creativity has come from the usage and the need. So again, further creativity, food prep, bartending. These are all applications that have happened out there, and they all require unique end-of-arm tooling. This is just one of my favorites. So we'll just watch this video real quick.
That gripper is very small, huh? The fingers on it.
It's just meant to latch.
Mm-hmm. Yeah, I'm noticing things that I haven't noticed in this video before, like what it just did there, where it actually
fingers just opened up
to
hold it.
Yep.
So it's like what they would consider an auto tool changer, and highly customized.
Yeah, and a multi-purpose gripper too.
Yep. And there is, on the UR Plus site, there is a gripper that does that. And maybe even Robotiq has something like that.
Well, actually, Dave, you got me thinking that the gripper we're showing today, there's nothing that says you couldn't just take the fingers off this gripper and switch them out and even customize them if you wanted
For
to.
sure.
Yeah.
For sure. I just think that omelet's maybe a little undercooked, but nonetheless, really cool how that's done.
Yep.
So yeah, creativity is really at the heart of for those of you that are getting into or looking at these designs, you've got to be creative, because most of these is nothing really off the shelf other than the foundation. You've got the robot, you've got a gripper, but even the fingers, as Adam was pointing out, are not designed that you get a standard set of fingers, but whatever it is you're picking up, in this case, picked up a spatula, picked up oil to turn it upside down. So you need to be creative in your approach, which is what we've done too. And these are some solutions that you're seeing that we provide to customers over time. What's really nice about these cobots is you can just roll these things right up to a table and work right next to something else. Again, no cages needed, and we can be really creative in how we go about designing these things, and really it comes down to learning. So that the usage applications drive the usage, they drive the creativity and learning. It's exciting stuff when students realize what they can do with these, and I'm just so excited to see what Essex Tech does as they get an opportunity to really start using their robots even more. A couple final last things about the robots, and for a lot of us that are here on this call, this is kind of where you guys are kind of the center of the universe when it comes to the robots and implementing them in your program. And these are kind of just some of the things I'd see you would be doing with the robot in your program. You might be determining like a return on investment for a project, designing end of arm tooling, jigs and fixtures for some kind of projects, special projects, material handling, and with the one thing about collaborative robots, the thing that you're not going to have with industrial robots is the frequency of deployment. The robot, when you make an investment in a universal robot or collaborative robot, you don't have to dedicate that robot to one specific task. The cost of putting an industrial robot in with guarding and everything else is going to really be kind of staying with the same application that you designed it for originally, because of what that cost is. With universal robots and collaborative robots in general, you don't have to do that because you can easily redeploy it. And that's a big part, I think, what I see here. And I think you'd be remiss if you didn't involve other departments within your school, other departments in general, like machine technology. You need to be the glue to all these different departments. But these are all the different areas. We've already looked at machine technology, metal fab, woodwork, and there are sanding applications, videography. Robots are being used in videography quite a bit, healthcare, and even culinary, as you saw. So, hey, and one last thing here. Universal Robots, AET Labs, we provide full solution, not only just the hardware, but training. I know a few people had asked about that, and there are great resources that Universal Robots provides. One is this E-Series Core Track training. It's an online program. You could go there right now, register for it, sign up for it. It's free of cost. Or to take your program to the next level, this is the skills certification program with Universal Robot. It's a hardware package, kind of like some of the ones you saw in those previous pictures. It's a certified instructor training program. It's got a curriculum that's 10 units, 32 hours. It is accredited as well, and we can certainly provide you more information on that. But that's my overview on that. I'm going to hand it back to Adam, unless anyone else has any questions.
Thanks, Dave. Yeah, if anybody has any questions on what Dave just covered, and you may have more, or you may add to those questions once you see the demo, but you can jump in at any point. All right, so I am going to switch over my video to my phone. Okay. And if anyone can't see my screen right now, or you don't have the robot on your screen, you can let us know. It should be up there for you. As Dave mentioned, yeah, we are at Essex North Shore Technical, what's the full name of the school? Essex North Shore Technical and Agricultural High School, I think, is the full term. And it's a really, really neat school. I love visiting this place. But right now I am in the metrology lab. And students were coming in and out using this profile projector earlier. It was pretty cool, but nice little spot. All right, let's jump into the demo here. So I'm going to show you a program right off the bat, and I do want you to see. Hold on, let me just do a quick little adjustment here. I do want you to quickly just, we're going to take a closer look at this, but I do want you to just quickly see what the interface looks like on the, what's called the Teach pendant, and the software is called Polyscope. So this is Universal Robots proprietary programming software, and it's a really elegant user interface that I've really enjoyed using. So we're going to take a look at this program tree a little bit more detail after we run the program. Okay, so first thing we're going to do, I'm going to go ahead and start the program. And just give you a little bit of an overview. And again, please, by all means, jump in if you have any specific questions. So what we're looking at now is the wrist camera flashing its light and looking for an object. In this case, it did not find an object, so it's going to see if it can find one to bring back over for itself, but it did not. So it just stopped the program. Now, if I throw down a USB stick and run the program again, this time it finds the object, picks it up, places it down, and comes back to look for another one. Didn't find one, so goes back over to look for one, and this time it does find one. And I'm going to slow this down a little bit. And what's neat about this is I'm just on the fly slowing down the program speed with a slider right down here. So notice I deliberately angled the gripper when it drops because I wanted it to drop the USB stick kind of in a random fashion, really to showcase how the gripper is, or I'm sorry, the wrist camera is detecting the object within its field of vision. And in this case, if we have a couple of objects, it will find both of them as it's denoted in my program. In this case, I said only to look for no more than 2 objects. And because it's going to pick up the other one, I'm going to want to remove this because it would just try to stack it on top. And at this point, you know, if I were in a classroom of students of any level, my next question would be like, how would I alter this program to make it more efficient? All right, so this is a pretty standard loop here, nothing too flashy about the programming, but what I am going to do is I'm going to change the dimension of the object that we're picking up. I have a few, sorry, I'm just stepping away for a second here. Yeah, okay. So I'm going to try to swap out the object when it doesn't find an object. I'm going to try swapping it out for this little brass piece of machine piece of brass here, which has a different dimension than the USB, just by probably 2 or 3 millimeters. So I'll let it run through its course here. And we'll see what happens when it tries to go pick this guy up. All right, so in this case, it did find an object there. It's going to go back to stopping. So notice there, it found the object because the thickness was too close here between the USB and the little brass component. But when it dropped it down and looked for it, it did not pick it up, right? So it definitely did a great job of distinguishing that this is not the USB stick shape. But this time, let's try running the program again. And instead of the USB stick, I'm going to swap it out for a pencil. Okay, so in this case, I programmed it to say, is it within a certain dimensional range? And if not, then open the gripper back up and let's stop the program because something's messed up here. Now, this is a great sample that we're looking at here. But when you're working in the classroom environment, in the lab environment, and let's say it is like you're onboarding people to the robotics, the UR robot system and the Robotiq grippers and wrist cameras, how do you bring this to the next stage? Like, what is this for? And I think, you know, what would be the application for this process? And since the Universal Robots is, you know, kind of exclusively marketed as a collaborative robot where people are interacting with it on a regular basis, I'm going to stop the program. And I'm even going to come back just a little bit to see if we can adjust this. So really meant to come in and on the fly, you know, change waypoints, move the robot around, make small adjustments. But what's the end goal here? In this case, if it was a collaborative robot and the point is I'm inspecting something or I'm doing like human inspection of this USB stick, and I am not really too concerned with manually palletizing these, maybe even on a plate, I can just more casually look at it and say, good, next, good, next, and have the vision system detect what I'm placing down. So I can kind of just quickly toss it over here. And that's just a small example. All right, let's go take a look at the program tree. Okay, so if you are familiar, if you are or aren't familiar with computer programming, Polyscope uses Python for its programming language, and it has like a specific kind of, I don't know what you would call it, like a buffer that changes the raw Python language to what you're seeing here. But you can write script, like custom script in Python. And something Dave and I were talking about actually is also our UR plus end effectors or end of arm tooling Robotiq gripper and wrist camera right here. They, essentially come pre-packed with what's called a UR cap. And that cap is, it's kind of like an app that runs in Polyscope here. And it comes pre-packed with all the custom script needed to run the peripheral and operate the peripheral. But let's take a closer look at what that looks like here. All right, so in our program tree here, some basics. We have a move command, which is just, saying, okay, let's do a start position. Let's make sure the gripper's open. And then we have this really fantastic cam locate node. And the cam locate node is exclusive to the Robotiq wrist camera. And what I would like to do is show you what programming this looks like. So we'll go to a new program. And we are going to go into our UR caps section here. Click on cam locate. And right away it populates this. And like this just looks like a few items here, but beneath this is tons and tons of script custom written by Robotiq for UR. So we'll click on teach object, and we're going to pick a calibration. In this case, earlier I made a calibration point for where we are now, the metrology lab. And we'll see what happens when I click and hold our go to snapshot position. That's what this is here. And that's just going to move the robot arm to a position where the camera, where I set it so it sees like a good area of my picking point right over here. The next thing I'm going to do is I'm going to place an object down. In this case, I'm just doing the USB stick again. And this, I did this I chose this very specifically, so a white piece of paper and a black USB stick, because when we're talking vision systems, that's a whole nother area of technology that you need to consider. So we have this like very low reflection matte white paper, and also like a fairly low reflectivity on this USB stick. So they're both great candidates to work together for the wrist camera to see the object. Okay. We're going to do the automatic method, but you can see that we have automatic and parametric or a CAD model, so you can import a CAD model. But today we're just doing automatic. Parametric, you're basically just entering in your dimensions, which make it a little bit easier for the robot, or more quickly find an object that's just like, let's say, a rectangular prism or a circle or a ring. All right, and now the light comes on the wrist camera to look for our object, and we see a nice little display of the camera here. We have some reflection here. Hopefully you can see this okay. And right away we see this green box around our object, which means it's done a good job of auto detecting it. If I wanted to, I could go into some more advanced features of the camera, and this is stuff that you would see in like if you actually dug into a camera app on your smartphone, or you were using a digital camera, exposure, focus, white balance, changing how bright your LED is, and so on. And that would just allow for you to work in different lighting conditions. So we'll say this is okay because it did find it. And here we have a close-up of what it exactly found. And it even shows us, see these little, you can see these little blue specks here. That actually is what the data or the pixels that are essentially required to look for the object. However, there's a bunch of stuff on the inside here that we don't need. We actually don't want to look for this. We just want to look for the outline of the object. So it makes it really easy for us to click on some tools and erase the blue sections or the blue pixels that we don't want to look for.
Can you just pick that up and kind of tilt it towards you just a little bit? Because I'm seeing a lot of reflection on the ceiling, I think.
Sure.
Just want to make sure.
Yeah, I don't know. I don't know if it's going to be better, honestly.
Yeah, I know. It's tough. I wasn't sure. Okay, yeah, that's actually.
Yeah.
I was trying to see what it was that. Yeah, that's better right there. At least gives people an idea to see it.
Yeah. Yep. Good. So So I'm just basically erasing all this midsection here because I don't want it to look for this. If I flipped over the USB stick, it wouldn't have that on the other side. It would just be looking for the edge. All right, so once we're good there.
There's a question from Patrick. I think he mentioned, can it find the printing? And I'm not sure if he meant the print, that was on that stick. Here. And I guess the answer is yes. I guess it can.
Yeah, it would be. It would be since this is also black in here. I think it would probably struggle if this was like a white lettering or even a white block. It would be much better. It's looking for contrast, right? That's the most important thing here. Is we need contrast.
But do you think is it possible that it could, if it was flipped over two different ways, if it had no writing, no printing on one side and had printing on the other, that would be some differentiation between the two. And so let's say it wanted to flip it over a certain way every time.
Sure.
It would know how to do that.
It's a variable, and it could be an unstable variable based on reflection, right? Yeah. So you could imagine if your USB stick, I'm grabbing the other one here, right? If this USB stick, you can even see right now when I tilt this, you can see the reflection of the light changing dramatically. And yeah, the camera, you would need to kind of create some specific conditions for that. But more to Patrick's question, I guess, is if you were you could put labels, or you could actually have an object that you had a specific type of printout on that was almost designed to work with the camera. And even more so, imagine getting into the territory of QR codes and barcodes. So the wrist camera, the Robotiq wrist camera, can absolutely read QR codes, and that's huge. That's like, you can go down a rabbit hole with that. But yeah, that's a great question. Okay, so we're going to click our selection, confirm our selection here. Let's see if I can change this a little bit. I might just end up holding the polyscope. Okay, and now it's asking me to do, for the automatic method, to do 4 different orientations. And at each orientation, we take a photo. And I think, I might, because this part can take a little bit of time. Let's see, hold on. There we go. That's how it should be working. So 4 orientation photos, and then it gives us a more detailed outline of what the camera's seeing. And what it's showing us here is green is kind of like valid detection pixels, and red is like, maybe not so good. But this actually doesn't look too bad. So we will click the check mark. And now it says robot will move automatically. And what it's going to do in automatic method, which is kind of neat, is it will move to different angle views of the part to get a better understanding of the dimensions of the piece. If we did parametric method, we would avoid this part. So the parametric method is actually, could potentially be a little bit faster, like if we had exact dimensions of this. Another interesting aspect to this method with this USB stick is this USB stick has like this little, right, it has this this section when it's open that's a different dimension in here. And if you noticed, our outline rendered by the camera did detect this. So when you see our program running, if the orientation is this way, the gripper might come in. Let me see if I could do this just by hand, but the gripper might come in like this and grab it, right, and move it away. But if the orientation is flipped like this, the gripper is going to turn, because that's how it was programmed. It was programmed with that specific orientation. On the other hand, if we're doing the parametric method and we're just saying this is just a rectangular prism with no distinct features, it will always go for the most efficient path, no matter which orientation. It'll just kind of come in and turn just a little bit. So yeah, really, really cool, cool, neat things to troubleshoot and problem solve when you're programming on this side of things. So right now it's doing 9 positions. It's on 7 of 9, which we have on the screen here. And once it finishes, it will tell us if it gathered enough, like all the positions look good and all the edge finding is really, that's like its biggest thing here is just finding the edge, because that's all we want it to find. It will tell us if it's valid, and we can move on to programming a pick and place. And this is what I just did earlier today when I was setting up the demo for you guys. All right, there's the last one. And our cam locate wizard is back here. I'll probably lift this up for you with some more features. And again, I love like Robotiq and UR just have these really great wizards that are start off nice and simple and then allow you to go stay simple or to get really, really into the kind of nuts and bolts of programming. So here is where I told the cam locate module to look for up to 2 objects. This is where I can actually do color validation, which is also pretty straightforward and easy to do, but that runs another section of the wizard. So let's say if I had a red USB and a black USB, I can absolutely have 2 separate routines that say, you know, if black USB is located, do this. If red is located, do this. And then you also have the option, oh, I know why it's not doing this, because it wants me to take a photo. So this is kind of our last validation photo, and it gives us an edge score of 99, which is really, really good. And there's the shape of our USB. And now I could go in and do color validation. I'm not going to do this one today. Oops. And this one would be, oh, I have to take a photo again. And gripper validation, or it's not gripper validation, I guess it's the clearance area. So collision validation, that's what it is. So here we can say, we can highlight an area where, so highlight model area in green. Gotta turn it on. Yep. So this automatically attributes like where it's going to be gripping. So what this would be about is if you had a USB, another USB in your field of vision that was with touching or inside of this red area, that's our gripper area, it wouldn't come down and grip this object. So it's a pretty neat feature that we can play around with and actually customize. Okay. Finally, we just take one final model position. It's kind of like our default model position. And it gives us a final readout. And we save that position. And now we can go in and say, if object is found, what are we going to do? And just to jump ahead here, let's open up risk can pick in place. So that's where we say cam locate for next object, do these moves. And if no objects found, do these moves. Any questions so far? I'm not looking at the chat. It doesn't look like there's any. Okay, so the other thing I wanted to show you was our gripper check. Which was happening at this point right here, right, where it comes down, and if it finds something, you know, pick it up. But again, you saw me put the pencil in, and when it goes to pick up the pencil, it's a no-go. All right, leaves it be. So let's take a look at that. Okay, so what we have, this is in if no object found, we have go do a series of moves up to the point of gripper close. And at gripper close, we have a grip check. And in grip check, we have if object is detected or not detected. And if we want, we can have an optional validate grip with dimension. So if I didn't have validate grip with dimension checked, then it would pick up anything that's there. So anything that's, you know, bigger than the gripper fully closed. But here I said close to 58%, which would translate to a dimension in this case. And if grip validated, do these moves, or else gripper open, so it doesn't pick anything up, and then just go back to the start position and stop the program. So pretty neat feature, grip check. Very easy to do too. It's literally, you're just putting your gripper action in there and putting grip check in. And on the gripper topic, another neat kind of feature we can take a look at is what our gripper actions look like. So you have three variables here: position, speed, and force. And and force, you can see I'm at 10% here. So let's say we're picking up objects like that are metal, we could certainly put force up to 100%. But if we're picking up something more delicate or fragile, we can bring our force down to all the way down to 1%. All right, and obviously speed and position too. So if you were going to demonstrate by picking up an egg, we would be really careful with our position here to make sure that it's not getting, you know, it's just getting to the point of the outside of the egg and just barely grasping onto it. And yeah, a couple other things you might have noticed. I put some like masking or painter's tape on the gripper. So with this material here of the USB, it was sticking a little bit to the gripper fingers. So that was a kind of a quick fix there. And when Dave was talking, giving his presentation, yeah, a great point came up when we were looking at the the omelet making, that was really like these two little, the gripper fingers were just two rods like that were maybe a half an inch or an inch long. And there's nothing stopping you from augmenting these fingers, and these like little rubber pads will come off, or swapping them out. You could machine, with your mill, a brand new set of gripper fingers if you wanted to. And it also comes, the kit itself comes with some different and replacements. I believe different sizes too. So pretty cool. I think that pretty much sums it up for the presentation.
Adam, I mean that the camera, I'll tell you, just adds just an incredible amount of diversity of what you can do for applications. I mean, you just touched upon just some of the basic things just for finding an object, but and a little bit of inspection. But man, you can do so much more with it.
I mean, I am, I'm still learning, and I am very excited to look more into using QR codes. And one thing that the RiskCam comes with is a small little QR code sample that is designed to be incorporated into your palletizing panel. And let's say you need to move it or augment it or something. As long as that QR code is kind of embedded in one location, if you moved it like up a few inches or it was angled or anything, you can say, if you see this QR code, I want you to adjust your work plane to accommodate for that, which is really neat.
I think another thing to point out too is going back to 3D printing. I think both of these technologies work out really well together, and that is, that the fingers, the end of arm tooling, right at the gripper themselves, where you had the orange tape. And a lot of applications, a lot of instances, those little plastic fingers you remove those, and they're underneath them there are little screw holes to attach your own custom fingers, because a lot of times you need to have that match what it is you're picking up. So those fingers by themselves are not enough, and that's where 3D printing, it just lends itself so well to 3D printing. And the thing I like about it too, and someone brought this up to me at one point, maybe not so much with collaborative robots, but even in a situation where you just don't want to damage whatever if something is really fragile, your 3D printing fingers or your transition plate that holds your gripper on there, you can make it so it's almost like a breakaway design. So if it did ever bottom out or hit something, that would break away before it would wreck your tool. You're
on mute.
Mute. We heard enough of you anyways.
Thanks, guys. That's what you're there for. Thank you so much. But I was saying that the Tormach mills we work with have the ATC, the automatic tool changers. They have breakaway components, right? Because sometimes you program something wrong and all of a sudden, it starts descending really fast, or something wasn't calibrated properly. So it's pretty neat. Yeah. Common thing, I think. Okay, well, I think we'll wrap it up. If there are no more questions, we really appreciate you folks joining us, and you can find us. I mean, you could really just reach out through the website. We can, I'll put my email in here. You can reach me there, and if you want to do anything from just ask some general questions to requesting kind of a full-blown demo, please reach out to us.
Thanks, Adam.
All right. Thank you, guys. And again, Pat, if you're on the call, thanks to Essex Tech again for hosting us. This has been great.
Thank you, guys.
All right. Bye-bye.